Good morning, everyone. So welcome back to QX01, Introduction to Quantum Information and its Associated Technologies. So let's have a look at the program first. So last week we looked at the qubit, finally. And today we're going to look at multiple qubits, because as we will see at a later stage, we need a lot of qubits in order to do anything useful. So multiple qubits will be important. And another notion that I already talked about, which is the notion of entanglement, which will be very important and key for quantum technologies. And then later on, so next week, measurements and operators, and then quantum gates. So all in this part are confirmed lectures up to this date, where there will be no lecture. And one of them will be given by a company, QX, on quantum cryptography at some point. So the program for today is quite intense. There will be a bit of everything, math and physics and computing. Not so much computing today, actually. So first I will talk about the definition of a multiple qubit. What does that mean? Then I will talk about the tensor product, which is a very important mathematical tool that will allow us to manipulate different qubits. Then I will talk about the notion of Hilbert space and how parallelism comes into play in quantum technologies, which is, again, at the heart of these special technologies. Then I will talk about entanglement, as promised, and talk about some of the physics that first triggered these ideas of entanglement and how we can use them. Then I will show you in practice how we can make a 2, 3, 4, and more qubit state in practice, so using an optical setup here. And then if I have time, I will, as I mentioned before, I will talk about the physical meaning of psi, because so far we discussed psi as a mathematical object, as a qubit, but we will see behind it that there's, of course, a physical meaning to it. Before that, I wasn't actually quite done last time on the qubit lecture, the lecture on qubits, because one part I haven't done is to talk about the dual space of the ket species. And the dual space of a ket is the bra dual qubit, as the product of the two will give us the bracket, and the famous bracket. So let's finish that off first. So for start, a reminder of the product of two matrices. So I've got two matrices here, A and B, and I want to get the product done to get the matrix C. So for that, we know, let me get a chalk first. So we've learned that when we were younger. So the way we can write it is A equals 1724. And then B, and usually I don't know how you learned it, but the way I learned it is to put it like this, where I've got 3352. So that would be B. And I want the product, C, which is A times B. And how we do that? Well, we take this line, we multiply it by this column, element by element. So that would be 1 times 3 plus 7 times 5, 1 times 3 plus 7 times 5. And then we take this one, this line, this row, multiplied by this column. So it would be 2 times 3 plus 4 times 5. And we carry on. For this one, it would be this row, this column. So that would be 1 times 3 plus 7 times 2, and then 2 times 3 plus 4 times 2. And that will give us, well, a certain number, so 338, and then in this case 626, and then 17, and then 11. Sorry, 14. Something like that. Anyway, I'm sure you can work this one out. So I want you to keep that in mind because we're going to use that a lot. So it's easy with a 2x2 matrix, matrices, but we will use the same rules for n by n matrices or even 1 by 1 matrices, which in this case will give us a number. And that's what, it's basically a row vector times a column vector, and that would be, say, this one times this one. So if I put it in, let's change colors. So if I take this one times this one, I obtain this one. And that is simply the scalar product. And so I don't know about you, but personally, when I was at school, the way I learned the scalar product was actually, now I find, the wrong way. Because usually, people would say, oh, well, scalar product is you take U times V, and you've got, I don't know, U1, U2, V1, V2, and you get the scalar product, which is this one times this one plus this one times this one. So, which is good. I mean, it's all right, we can do that. But turns out that there's a notation, which is to use the scalar product as a product of a row vector and a column vector. And for what we want to do, for how to manipulate qubits and Ketz and Bra, this is crucial. We need that. So the way we should have done it, really, is to say, well, there is right and left, and it's not quite the same, because so this one is a column, but this one is a row. So in fact, the way I should write it is more something like this, where I apply the same rule as earlier for the matrices, which we do learn that way, I believe, but just for a 1 by 1 product of matrices. And so in this case, we can identify this row vector, or line vector, depends on where you look, as the sometimes dual vector. And ideally, what would be nice is to have a notation for it, so that we know that there is a difference between right and left. So that right is a column, and left is a row. So we can put a sign, so say a T, to say that now if I take two vectors, I put a T here for transposition, for transpose, to say that this one is a vector as well, like this one, but not a column vector. It's a row vector. So it's like, I talked about the emission matrices where you take the transpose, you take the symmetry compared to the diagonal. Well, so here's the same. So you take your column vector and you transpose it to a row vector. So in fact, the way we should have learned it, really, is like this. But it's all right, never mind. We can relearn things. And now, as we saw last week, we said, well, a qubit can be identified as a vector. So a ket can be identified as a column vector. Then I can now define the bra associated to it, which is the transpose of the ket. Right? So here, this scalar product, if I use the bracket notation, would look like something like this, where I have psi times phi, which is basically, you take the ket, you take the bra, which is the reverse ket, and you just bring them together. And that's a new scalar product, which you can write like this. I mean, no need to put two bars, one is enough. And this is a scalar product, which we also call, which can also call an inner product. Okay, so now, oops. So now, again, so this is the ket, and this is the bra. So this could be written like this, and this could be written like this, and the scalar product of the two can be written like this. Same thing. Right. So this is very important, and let's just keep that in mind for the following. Because there's a second ingredient that we need. You remember we said that all of this, all of our qubit space, all of our physical space, has complex numbers and has coefficients. So these numbers here in the scalar product, they're actually complex numbers. And we talked about Hermitian matrices as a physical system, and somehow we need to apply this to the whole space that we work on. So for that means that we can do the same thing as we did here, except that now there is some form of double non-symmetry, or two non-symmetries, between right and left. Is that left is the transpose of right, but it's also the complex conjugate of right, as you can see here. So in fact, what we want when we work with Hilbert spaces, which we're going to talk about in a minute, is that so let's write it. So let's make some space, if I can find something to erase there. So let's assume I have psi, the ket psi. So the ket psi, I can write it as in alpha beta, like this. We saw that before. And I can take phi, which is going to be gamma delta. Oops. No, sorry. Gamma delta. And now, following these rules we just saw, I want to take the inner product. I want to do the scalar product, which we will call inner product between the two. So in order to do that, we need to transform this guy into a row vector. So we need to transpose it from a column to a vector. So, and we will write it in a bra notation. So it will look like this. Because the scalar product, the inner product at the end, and we say, is this. This is what I want. So I need to take psi, transpose it, and, second rule, take the complex conjugate. Remember, we talked about this with matrices when we talked about emission matrices. There are two operations which we call the dagger operation. The dagger operation is transpose and then complex conjugate. That's what we need to do here as well. And then this is it. So alpha star, beta star times gamma delta. And that will be alpha star gamma plus beta star delta. So all of this, by the way, in mathematical terms, is what we call a sesquilinear form. But this is not so relevant. What is relevant, though, as we will see later on, perhaps not today, but next time for sure, is that, so this is what we call a sesquilinear form, but this form can also be applied, so with the same properties that we will see, to integral product. So if we were to write this bracket notation as so this inner product as an integral between psi star times phi over the whole volume, d tau. So let's put we can even put a triple integral. Then you can show that there is exactly the same properties mathematically between the two, and that everything I'm going to talk about with bracket notation and matrices and Hermitian matrices and so on can apply the same way to integrals. The big difference, though, is that this is a very convenient way, mathematical representation, that we will use mostly. But this actually has a physical meaning to it. There's actually physics behind that. Okay? So I'll get back to that later. So let's carry on. So now we have the dual space and the bra concept. Then all you have to do is read the field manual. RTFM, read the field manual. With some properties and some rules and some notations. So the first one is, well, I mentioned that already, is when you go from a ket to a bra, what you do is you do the dagger operation. Remember, the dagger operation is the transpose, dagger, write it down again. So the dagger is the transpose and complex conjugate. So basically, to go from this guy, which is a ket, to a bra, you need to apply the dagger operation, which is this. So in other words, the bra here is equal to the daggered ket. Okay? If phi equals psi, then what we have here is a norm. It's the norm of the ket vector, the column vector, or the row ket bracket vector, or quantity. So we can define a norm. There we go. This is the norm. This is the norm of psi, the ket psi, which is a positive quantity. And we can define the null vector. If psi is 0, then the scalar product is 0. And as we said early on, we like to have normalized qubits. Remember, we said we like to have normalization on these vectors. Well, that means the vector squared, so psi, bracket psi, is equal to 1. So that means that alpha star alpha plus beta star beta, which is alpha squared, plus beta squared is 1. So it's normalized. We have, at the end of the day, and the parallel with vectors is still holds, so we can have orthogonal vectors or orthogonal brackets. So if Vi and Vj are orthogonal, then the inner product is 0, and if they are equal, the inner product is 1, if it's a normalized quantity. So I put here as a preview, we defined an inner product, but we can also define an outer product, which is the other way. It's the ket times the bra, not the bra times the ket. And I'll let you work out what that makes, okay, for next time. Right, let's carry on. We have commutativity. If we add 2 kets, then we have another one, which we usually don't write like this, but we could. This is another type of notation. We have associativity. We have a null vector. I can always define a null vector, 0, nothing. I can define an inverse element, which is the case for vectors. I can have V and minus V. So the sum of the two is 0. I have what's called closure, meaning that if I take a ket and I times it a lambda, which is a complex number, then I have another ket, surely. I have distributivity. I have number product, which is another way of saying closure. And I have an identity. I have an operator, which in this case is a matrix, by the way, which is the identity matrix, which doesn't change, which doesn't change the ket to itself. And then we have some more. So I'm not going to go through all of them. I'll let you enjoy them. I just want to focus on 2 properties, knowing that all of those properties can be derived from all of what I showed before. But 2 properties. The first one is that if you apply the dagger to lambda times the ket phi, then you have, we said, the bra associated, but you also have a number lambda that has to have something to it, a transpose to it. A transpose of a number is himself, but it's a dagger operation, so it's a transpose and a complex conjugate. So when I go from this quantity to this one, I have lambda star times the bra. Okay? Which you can derive basically from this rule here, from the closure rule. The second property that is a very physical property that we won't use much for quantum technologies is the fact that all of this is what we call a linear space. So this is our Hilbert, form a linear space, a Hilbert space that we will talk about. And is all, in this case, is all with given vectors, with given dimensions. But we can also have the same space with continuous variables, continuous dimension, infinite dimension. In this case, if we talk about the scalar product or the inner product between a bra and a ket, then rather than having the Kronecker symbol, delta ij, we would have the Dirac function, delta alpha minus alpha prime. But same idea. Again, this has a very physical meaning, which for quantum technologies is not used so much, but it's an important property as well. And as we will see, I already mentioned it, but this mathematical representation, phi psi, as actually can be written in another mathematical representation, which is the integral of phi star times psi. But this has a physical meaning. Because this psi here is what we call the wave function of the system. The wave function of the system is basically what characterizes in physics the system. So a photon has a wave function, an electron has a wave function, you have a wave function, I have a wave function. Everyone has a wave function. Everything has a wave function. So there is a physical meaning, which is a quantity that describes a system as a function of the position and time. So there is a physical meaning behind all of this. This is not that quantum theory, but this is quantum physics. Again, this is a preview. We will see that hopefully today, otherwise next week. We'll come back to that. Right. So, okay, so multiple qubits and entanglement, and let's move on. So we have all of this, as I said already. And let's start with the definition of a multiple qubit. Before that, I just want, again, you to keep in mind this rule that row-column vectors, this multiplication of matrices, that there are dimensions associated to it, there are rules. Okay, fine. But what's important is that now, so far, we've defined column vectors, we've defined row vectors or line vectors, we've defined inner product. We also saw emission matrices and how to multiply them. And there are two more important mathematical concepts, but which again have a physical meaning behind, but for quantum technologies, they're important. It's the notion of tensor product, which we're about to see, and the notion of outer product, which I sort of hinted earlier as a preview for next time. So, first, definition of a multiple qubits. So multiple qubit means several qubits. So here is the ket, or the wave function, of 2 qubits. 2 qubits is, so each qubit can take the value 0, 1. So 2 qubits can take the values also 0, 1. And 2 together, the most general state will be this state, where we have 0, 0, 0, 1, 1, 0, and 1, 1. Right? With 4 coefficients, and all of them, in the most general case, in a superposition state, that all of them are possible. Okay? And so this 0, 0, 0, 1, 1, 0, and 1, 1 is the equivalent of having two classical bits, where you could have, if you take 2 transistors, you can have 0, 0, you can have 0, 1, you can have 1, 0, or 1, 1. Except that if you have 2 transistors, 2 classical transistors, you only get one of these 4 results. There are 4 outputs possible, but you only get 1. Here, like we said for a single qubit, where you can have, so for a classical bit, you only have 0 or 1. A qubit, you can have 0 and 1. Well, for 2 qubits, you can have 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time. With 4 coefficients, so I can call them alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. With the same properties that we saw, so these coefficients are complex numbers. Again, this multiple qubit state will be normalized, so there is normalization factor, but let's not worry about this for now. But what's important is that I can rewrite this state, this ket, this vector state, as a column vector, like before, except that now you can see that our column vector is not 2D, but is 4D. With the 4 coefficients and with the 4D vectors associated to it, so 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1 being the coefficients of these 4 vectors. These 4 kits. Okay? Okay, so that's 2 qubits. And that's what it would look like for 3 qubits. So in this case, I've got 0, 0, 0, 0, 0, 1, and so on and so forth, up to 1, 1, 1, with 8 coefficients, all complex numbers, and an 8-dimension vector. I mean, 8-element vector. Okay? And that already, I mentioned that before, but that already gives us the power behind that. Because in other words, it means that for n qubits, so here so far we've seen 1, 2, and 3, I've got 2 to the power of n vector, right? Because for 1 qubit, I've got 2D vector. For 2 qubits, I've got a 4D vector here. And for 3 qubits, I've got an 8 number vector. So I have 2 to the power of n. If I take transistors, n transistors, what I end up with is n outcomes. It's a linear behavior. If I add 1 transistor, I only have n plus 1 computation power. But here, if I have n qubits and I had 1 qubit, one more, so I go from n to n plus 1, now I've got 2 to the power of n plus 1, so I've got twice as much computing power. That's not bad. Right, so how do we manipulate these objects? For that, we need what's called the tensor product. So the tensor product is a bit particular, but again, you know, it's like Cluedo, Monopoly. You've got rules, just apply the rules. So let's see what this tensor product does. So the tensor product, so let's consider two qubits, 2 kets, so phi, which is, so I put alpha 0, 0, plus alpha 1, 1, and psi, which is beta 0, 0, plus beta 1, 1. So if I want to form this new 2-qubit ket, 2-qubit state, so something like this, which is not quite, it's not the inner product, right? It's not quite multiplication that we saw before, because we saw it before, the multiplication as such of 2, first of all, we didn't write it like this, we wrote the bra and the ket for the inner product. So here is different. So we need yet another symbol, which is this symbol. For the tensor product. So I don't know what came first, whether it was the X-men or the tensor product. But the fact is, this is what we use to say that this is an operation that is different than the inner product. And we can see clearly it's different because the inner product, or the scalar product, the equivalent, is this operation, which we wrote like this. So it's different than this one. And it means also there are different rules. So now in this case, I can write the two columns like we learned when we were younger for the scalar product. And I can write it like this with this tensor product sign. And I've got this operation. And the result is multiplication of coefficients. But as you can see, in a specific way where you take the first coefficient and you time it by this, the whole vector of psi. Then you take the second coefficient and you time it again by the same, using the same column vector. And then what you do is simply a number, so say alpha 0, times a 2D vector, and that we know what it does. It just transforms it into another 2D vector, which is alpha 0, beta 0, and alpha 0, beta 1. Except that now there's a second operation here to do, which means that this adds the two other components, which gives us a 4-term vector now, not just 2 or 1. Right? So you can write it like this with alpha 0 times beta 0, beta 1, and that's a standard multiplication. And this one, which is going to give us the 4-component column vector, which is this one. Okay? So those are the 4 coefficients. And if I talk about, so these qubits, so 0, 1, 0, 1, and 0, 1. So what I have here, what I've done here really, is that I multiply this one by this one, which is that I multiply this ket by this ket, or I took the tensor product of these two, like that. Okay. So now let's put it here. No, let's not, sorry. Let's not put equal because it's not. This is the component where we have this. This is a component where we have this. And this is a component where we have, where we have this. And this is a component where we have this. And like we saw before in the rules of the manual, we can write this just simply like this. This one as being 0, 1, this one as being 1, 0, and this one as being 1, 1. So this tensor product at the end will be alpha 0, beta 0, 0, 0, alpha 0, beta 1, 0, 1, and so on, which I can rewrite using the rules that we said before, where, so again here I could also write this as being something like this, or something like this. These are all equivalent notations. If I do that, then I end up with 0, 0, 0, 1, 1, 0, 1, 1, which is the definition of our 2 qubit vector. So you have all sorts of notations that you can see. So this is equivalent to this, as we say. Sometimes there are also this notation, which I particularly do not like, but does exist. And you can carry on with 3, so 0, 1, 1 gives 0, 1, 1, like we saw before, for 3 qubits, 3-qubit vector. And so on and so forth. Okay. But the good thing about the tensor product, as you can see here, is that I can apply the distributivity rule that we know from before, which is that this times this equals to this, which is a distributivity of A plus B times C plus D equals A times C plus A times D plus B times C plus B times D. I can do the same. In fact, that's what I did here. And I end up with this. We'll get used to that eventually. So let's do 3 qubits. Well, 3 qubits, same thing. Alpha 0, alpha 1, beta 0, beta 1, gamma 0, gamma 1. So we've got these two first, which is this one. But now we have to times this times another vector, which is gamma 0, gamma 1. So we take each of these coefficients and we time it, this vector. So that makes this term, this term, this term, and this term. And each of them has 2 terms, so that makes our 8 terms. From alpha 0, beta 0, gamma 0, up to or down to alpha 1, beta 1, gamma 1. Which we can rewrite, so I'm not going to do it here. That's a good exercise to this state that we put up earlier as being a 3-qubit state. Okay. One quick note, because it's a useful note, is I don't know, but I never know which order to put the 0, 0, 0, 0, 1, 0. You could say it doesn't matter really, you can put any order, and it's true. But when you talk about people people in the field, some of them are mathematicians, some of them are computer scientists, and some of them are particular physicists. So they say, no, hang on, you can't just do that. You've got to have some order. So the order is very simple. It's the order of the binary system. And also, now it's the physicist who's speaking, so I don't do binary every day, but the way I remember is I can do binary on my hand. So 0, 0, 0 in binary is 0, okay? 0, 0, 1 in binary is 1, because it's 1 times 2 to the power of 0, which is 1. So this is 1. And then this one is 2, so is this one, this finger, because this is the 2 to the power of 0, this is the 2 to the power of 1, this is the 2 to the power of 2, 3, and 4. So this is 0, 0, 0, this is 0, 0, 1, this is 0, 1, 0, this is, this is 0, 1, 1, then this is not just root, but it's also 1, 0, 0, and then 1, 1, 0, 1, 1, 0, and 1, 1, 1. Okay? So again, 0, 1, 2, 3, 4, 5, 6, 7, 8. I must have missed one. But you got the idea. Okay? No, 7. That's 7. So that's the order you have to put it. In fact, it doesn't really matter, but at least there is some form of order so that people know in which order to put them, especially that we will see for the notion of entanglement that we can use the power of multi-qubits without to have the entire coefficients being non-zero. because that would make it complicated. But we'll see that later on. Right. So what we basically define here in this last almost hour or so is the definition of a Hilbert space. So what is a Hilbert space? A Hilbert space is a vector space or linear space, depends, it's the same, as far as I'm concerned, it's the same thing, with an inner product. We define that. This is the inner product here. In the complex number field, we said that we have complex numbers, we have this dagger operation. So Hilbert spaces can be finite, and that's what we have here, and that's what we are mostly going to manipulate in QX01, and that's what we need for quantum technologies. Well, it's easier to manipulate finite spaces with the qubit 01, and then 1 qubit, 2 qubits, n qubits. But as I said, there is a physical meaning to it, of this Hilbert space, and an Hilbert space can also be an infinite space, infinite dimension. We won't use it so much in this course, but we do need that a lot in quantum mechanics, quantum physics. So here's our 2D Hilbert space, is 1 qubit. Here's our 4D Hilbert space, is 2 qubits, and then 3 qubits, and so on and so forth. With the rule that there are dimensions with the tensor product, as we saw, which is the dimension n of the tensor product between these 2 qubits will be the product of the two. So earlier, I talked about the notion of parallelism, and here we see the power of parallelism in quantum technologies. We see how this parallellator or superposator, whatever that would be called, makes a crucial exponential increase in the power computing, the computing power, sorry. If we take one transistor, classical transistor, I've got 0 or 1 outcome, only have one outcome. If I take a qubit, I have a superposition, I've got 0 plus 1 outcome, so 2 outcomes. Two bits, 1, 1, 1, 0, 0, 0, 0, 1, but I only have 2 outcomes, measurements of my 2 transistors. For 2 qubits, I've got the superposition of the 4, so I've got 4 outcomes, and so on and so forth. So n bits scales as n, but n qubits, as we said, scales at 2 to the power of n. So we see straight away here how we the addition of 1 qubit is a tremendous power increase in computation. To give you an idea, if tomorrow I were to have 51 qubits only, 2 to the power of 51 gives few 10 to the power 15 in terms of power. So we're talking about petascale computation, which is the current computation power, where you would need an equivalent of 10 to the 15 bits in a computer in order to be as efficient as 51 qubits. So all you need is 51 qubits. So if tomorrow you can get 51 qubits working, then that's it. You've outcome any computer that exists right now. And if you have 52 qubits, then you times this by 2, by just adding 1 qubit, and so on and so forth. And very quickly, it's exponential, you'll be much better than any computer that we will be able to make for the next hundreds of years, perhaps even ever. And there are technologies, so here I put some, that try to do that. So to work on hardware to build these computers. So here I just put 4 examples. I don't have any any particular interest in any of them, just some different technologies. So IBM use superconducting qubits, which we said we're not going to talk much about, but at some point at the end of QX01, we will talk about the various physical technologies. We'll come back to that. There is also, for instance, IonQ, which is a startup company, American startup company, who used trapped ion qubits, so single atomic ions trapped in an electromagnetic trap. You've got silicon quantum computers, this company, where they manipulate, and we'll get back to this system. Remember, I'll say I will use two physical systems, so photons and spins in electrons. So I haven't talked about this one yet, but I will. So that's what they do. They manipulate electron spins inside silicon. You've got this startup company called Pascal, which uses neutral atom qubits. So the idea is also to trap atoms, but those are neutral atoms, so you can do different things than you can do with trapped ions, and so on and so forth. And you could say, well, that's it, it's done, so we've got computers, here we go, we've got 4 of them. Well, it's not that simple. So maybe we will have time during the semester to touch that. But in order to get, when I say we need 51 qubits, we will talk about this later, we need 51 very, very clean qubits. Clean meaning no error, or there is no such thing as no error in physics or in life, but very low rate, very, very low error rate. And no, so far, no, there is no technology that can operate with that many qubits, with that many qubits, with the right error rate. So the race is still on, okay? And that's what is at the heart of the technologies behind, is to be able to fabricate these qubits, and to fabricate them not just to make them, but to make them with the right properties, and especially to make them clean, pure as much as possible, without error. Whatever that means for now, we will get back to that later. Right. So now I want to go to the very important notion, which is the notion of entanglement that I already talked about this in the first lecture. So in fact, if I take 2 qubits, so phi and psi, and if I take the tensor product, like I did here, I have this state, okay, with these coefficients. So if I take alpha, beta, gamma, delta, then I've got these 4 coefficients, 4 terms, which I can rewrite A, B, C, D. And so this is good, this is the definition, but the thing is, this particular state is in fact a very, very particular state, and that's what we call a factorizable state. A factorizable state means that it is a state, so it is a 4D vector, that can be written as the product of the other 2, product in a tensor product sense. But also product as a product sense, multiplication sense. But the thing is, you can see that these coefficients are linked, one with each other. A equals alpha gamma, but is also B divided by delta gamma. And C and A are related, and so on and so forth. So it means that if I change any of these coefficients, so if I take one out, say alpha equals 0, for instance, then I got another state, which is, so if I take alpha equals 0, I haven't put it here, but it would be, which one? I'm lost. It would be 1, 0, and 1, 1. But I can take any combination of these 4 states, and make it this one, for instance, which is B01 plus C10, or A00 plus B01 plus C10, or A00, B, and so on. Same thing, but with a minus sign here. And as soon as I do any of these things, any changes out of this particular, very, very particular case, then what I end up with is a non-factorizable state. I end up with an entangled state between the two qubits. Something that cannot, that link the two qubits together in a very, very particular way, which makes a system of the two, which is a whole system, which cannot be seen as the multiplication or the juxtaposition of the two systems separately. And that's an entangled state. And that's very strong, because that means now these two qubits, so in any of those states, this one, this one, this one, and there's an infinity of them. Of course, we will see that we are going to use particular ones, which we call Bell states. But you can see, so that any of those is an entangled state and has this specific property that now you intertwine these two states together, these two qubits together, in a unique way. So the definition of an entangled state is a non-definition, in the sense that an entangled state, so two qubits are entangled if they cannot be written as the product of the two separately. And that's what you have here for those. For this one, no, but that's the particular case. That's the only case. Which means, by the way, I told you in physics there is no such thing as no error, no infinity, no zero. So that means that if we do want to implement this physically, then this state is impossible, or next to impossible. Because those coefficients, one of those, because one of the operations, one of the errors will be in the qubit, will make this impossible to solve. So in fact, this state is almost impossible. So in fact, by default, you get an entangled state whether you want it or not. So better want it and try to control that. And that's what people try to do, to make entangled states, such as this one, which is the simplest you can have for a 2-qubit entanglement, and try to get that one nicely done, for instance. So this is a very sort of mathematical description. Well, not very, actually. There's a lot more mathematical description behind it, but I don't think this is very necessary. But there is a physical meaning to it, again, and that comes back to 1935, where these three people, and you certainly know one of them, not personally. So these three people came up with the so-called Einstein-Podolsky-Rosen paradox, also called the EPR paradox, which is that they precisely looked at a quantum system. Now we talk about quantum physics. A quantum system where you would have two physical particles, and you would, by some experimental means that they had no idea at the time how to do that, but they say in practice, you could have such a state like this between, so 0 and 1, we talked about the polarization state of a photon, for instance. So you could have these two photons, and with each of them has its own polarization, but the two of them are entangled and have this property. We'll get back to that later, but they have this property. So that means that you could create what sometimes is called now an EPR source. Well, not now, actually, not so much anymore. It used to be used, it's a term that was used in the 80s and 90s more than now, but still you can find it, where an EPR source would be a source of two particles, quantum systems, that you entangle together. So you would have a whole system with two physically separated systems. You could have one, and I can get the other one. So I could have one on Earth and take the other one to the moon. And they would be, by their creation, they would be entangled together. That means that the system is a non-separable state. So if I want to write it in terms of polarization of a photon, for instance, I would have to write it like this, which is not a factorizable state. That means I would have correlations between the two that are instantaneous in a way. Because when they've been created, once they're separated, they still keep these entanglement properties, no matter how far apart they are. And that would mean, and that's what really bothered Einstein at the time, it would mean that you can have correlations between two systems that is faster than light, that is instantaneous. And in physics, physics tells you that nothing is instantaneous. There is no such thing, because nothing can go faster than the speed of light, or at least as far as we know now. So these three people came up, so they call this, so it was a German term, but the translation is something like a spooky action at a distance, because that means that now if I manipulate my photon here, my particle here, as it is entangled with this one here, I will change the state of this one here without even doing anything to it, because I did something to this one. And that was not on for these three people. And that's where Einstein, or this EPR, said, well, the quantum mechanics somehow is not complete. There's something wrong with it. It's got to have something else, because you have to have what is called hidden variables. You have to have something underlying everything which knows what to do in advance, right? Because there is this faster than light, or looks like faster than light, transmission of information between the two. So they have what we call a locality issue, where whatever you do here, whatever you do there, will influence the other place. And that is a big problem. Because once again, in physics, things are usually that if I do something here, it might affect something there, but there is sometimes it takes some time to go from here to there. At the fastest is the speed of light. So the solution, or at least the quick solution, is to say, well, the mistake is to actually see this entangled state as being yet is two separated objects, but to see these as two separated objects. Because they're not. What they are is it's what you can define is a global wave function. Remember I talked about this wave function, I'll come back to that later, which defines every system, except that now the wave function of the system is not the wave function of system on Earth and system on the moon. It's the wave function of system of the two of them. Whether they're spatially separated, that's irrelevant. It's just a fact. So that was a very physical, physical notion that EPR came about. Since then, we have no problem with that. And since then, so another physicist, so John Graham Bell, came along and showed, so I'm not going to do that, but showed that there is no problem with quantum mechanics. There's no hidden variables. There's no mystery between all of this, because, well, quantum mechanics is what it is. You have a global wave function for the two. I can define that. I can define, so if I have two, in this case, two qubits with 0 or 1 property, I can define, so in this case, what we call the 4 Bell states. Those are the 4 Bell states. So we will see later on why we use those, but those are particular states that we like to use. One reason is because they are so-called maximally entangled states, and we'll come back to that later. They are non-factorizable states. They are not, I cannot write this state as being the product of the two systems separately. It's really the wave function, the ket of the two systems together. They could be separated spatially, that's okay, there's no problem. But the fact is that in order to define them, I have only one quantity, one notion, one physical implementation of it, which is the wave function of the two. So a non-factorizable state is not measurable only locally. In other words, and this very important properties is used these days for quantum key distribution, for quantum cryptography. Because now you can see that if we have an entangled state, and usually for quantum cryptography is done with photons precisely, if I give you one photon and I keep the other one, you and I have now a unique correlation between us, a unique entangled state between us, because it's a unique state between the two photons. That's the so-called Eckert protocol that I mentioned in the first lecture. There are other ways of doing quantum cryptography, but this one is the one where you use two entangled photons in such a way. So again, I'll tell you later, probably next week, one way of doing it in the lab using photons, and at some point, not next week, later on, much later on in the semester, I will show you an experiment on how you do that, so with photons. So, bottom line is that entanglement is not easy to create experimentally at all. It's very, very difficult. But once you do it, you're on for the race. And we will see, so this is a very physical description. We will see next week and the week after that, how we manipulate that in terms of computing, quantum computation, using the so-called entangling gate, which is one of the gates which we call the C0 gate, control NOT gate, which is a 2-qubit gate. So it's a 4x4 matrix, because 2-qubit gate is a 4-dimension vector. It's a 4x4 matrix that will take 2 qubits that are separated first, that are factorizable, and then entangle them together into a 2-qubit entangled state. And so the control NOT gate, or C0 gate, between 2 qubits is sometimes called the entangling gate, and is used in computation to, well, basically, to build our Hilbert space and to make it growing as n grows, number of qubits. Then the space will grow as 2 to the power of n. Right. So let me show you now how we can, in practice, how we can make a qubit state, and how we can also see how this qubit state can be seen as an entangled state. So for that, let's go back to some physics. So let me erase all of this. So if you have any background in physics, you must have heard of the Young's experiment, interference experiment. When you take 2 slits or 2 small holes in an aperture, and you send light to it, and you look at the pattern that comes out. So here is the experiment. so I've got a source of light here. So in this case, I will show you, I will use a laser. I have two holes. So in this case, what I have is two slits, but same idea. And I have a screen. And I look at what comes out of it. And what comes out of it is a pattern like this, which is an interference pattern between bright spots. Oh, this is not quite in phase, but between bright spot and dark spots. Those are interferences. And the intensity, so if you were to come, so here on this screen, if you were to come with a power meter, something that measures the light intensity, you would see, you can reconstruct exactly that curve like this. Okay? And as a reminder, we will do it. You can show that the intensity here is equal to the intensity emitted by the hole or the slit 1 plus the intensity emitted by the slit 2 plus a term which is square root of I1, I2 sine theta, where theta is due to a dephasing. So let me explain that. If you remember when we talk about photons, we said that, so without going, let's go back to light first before photons. So light is an EM wave, electromagnetic wave, which we can define as being what the electric field does, E. And we said we can simply take, for light, a solution of these Maxwell's equations, whatever. We said, well, we can just simply take a plane wave. So oscillation function of time and space. So let's do that. So I can do that. And in so let's say it's along, I don't know, the Z, along the Z direction. So that would be E1, which is the electric field that comes out from the hole 1, this aperture. And here, I would have the same thing. Let's assume also, we don't have to, in fact, let's not do it. So, different amplitudes. We don't have to do that, doesn't matter. So it would be the same thing, except not. Because we mentioned that already, we saw it briefly. So again, it's not a lecture on optics. I'm not going to go back into some optics. But all I can say is that these two will not be exactly the same, because, for instance, if I take this point here, you can see that the electric field, so the light propagating from this point to this point, is different in a sense that he goes faster than this one that goes from this point to the same point. Right? There is a distance added to it. This distance added to it in terms of wave propagation means that when you had two synchronized waves, now one goes faster and the other one has to catch up. So there will be a dephasing, right? Because one has to take a longer path. So it will be a dephasing. So they were in phase first, and now they're not. So how do I define this? I say, well, okay, so I can say that this one is dephased compared to this one by, I don't know, say theta. which would be dephasing due to the fact that, again, if these two goes so next to each other, they go straight, no problem, they're not dephased. But if I want to look at when these two arrive on the screen on the left, then you can see that this one is going to arrive before this one. So there is a desynchronization, desync between the two. How we do that in optics, without going into details, we'll say, fine, we just add a phase, theta. Good. So now, one definition is that I is the intensity on the screen. And this in a lab is what we measure. We don't measure electric fields. We measure an intensity with a power meter, like here. If I want to know how much light there is coming into my face right now, then I'd use a power meter. And I'd measure the power of light, or the intensity, which is related to the power by the surface, but whatever, that's what I measure. And how is this linked to the electric field? Well, the intensity I is a constant, say K, whatever, times the, so as we are in complex notation, times the total electric field squared. So, by the way, I'm getting back to that. So in this case, we have a plane wave in complex notation with a frequency omega and a wave vector, propagation vector k, along, in this case, so going from the slits up to the screen, and say along the z direction. So this is the total intensity. And the electric field, the total electric field on the screen is the two, due to S1 and S2, the two sources, the two slits. So it's E1 plus E2 modulus squared. Right? So let's do this. So it's basically K times E star 1 plus E star 2 times E1 plus E2. Right? Okay, so what that makes is I equals K E2. So again, this is just a constant that doesn't have much meaning here, so let's not worry about this. And so what that makes is K times this, plus this times this, plus this times this, plus this times this. So let's go. This times this is modulo squared, is the squared, the modulo squared of E1. So this is E1 plus this times this, which is E1 star E2 plus E2 complex conjugate E1 plus E2 star squared. Okay. Good. Well, this I know. Now if I distribute K, this I know. Let's take some colors. Pink. This is I1. By the same definition as that is I1, which is what? Which is basically the intensity that I would get on my screen here if I were to have S1 alone, without this one. If I were to have S1 alone, then I would have electric field E1, and I would end up here with an intensity I1, which is, I don't know what, a blob, probably, that would look like K E1 squared. So this is I1. And this, or times K, is I2. So I equals I1 plus I2. And now I have the cross terms. And those are the interesting ones, because those are the ones that are going to give me this factor here. Okay? So let's see what it looks like. So E1 star times, with the K, E2, plus K E2 star times E1, and that's it. So now let's go for it. E1 is this, E1 star is just a complex conjugate, and E2 is this, and E2 star is a complex conjugate of that. So that would be I1 plus I2. If I take E1 star and E2, I'm going to multiply the complex conjugate of this times this. Everything goes away except I theta. So I have plus K E01, E02 exponential I theta plus the other, so this one complex conjugate, so minus all of this times this. Everything goes except the exponential minus I theta. So plus K. One assumption I make here is I assume that those are real, by the way. I don't have to, but it doesn't matter really, as we will see. So times E01, E02, and this. Right. Okay. So now I can take that, I can pull it out, and I would have, so let's write this, K E01, E02, exponential I theta plus exponential minus I theta. And I can write this as saying, well, this is what? This is 2 sine theta. Sorry, cosine theta. There is a mistake there, but it doesn't matter. 2 times cos theta. And this is my interference term, which is the one that's going to give me these oscillations. I can rewrite this as well as a function of I1 and I2. So let's do that. I'm going to erase this. I will probably regret it, but all right. There you go. Yep, I already regret it, but it's all right. So I equals I1 plus I2 plus K E01, E02 times 2 cos theta, right? And we said that I1 is K E1 star which is actually, forget the complex number, so it's actually k is 1 squared. And I2 is k is 2 squared. Okay. Right. So in other words, the case will probably bother me, but at the end, let's not worry about this. We have I1 plus I2 plus 2 square root of I1, I2 cos theta. If you carry on. So two changes to be made here. There should be a 2 here, and there should be a cosine. Actually, it could be a sine theta, doesn't matter. In this case, it's cosine, but it's just a phase term. It's not a big deal. The physics is the same in the sense that this term here, and I will show you how we do that, this term here is responsible for the interferences here. This is what gives the interferences. Okay? So let's see how we do that. So I have a laser here, and I have 2 elements. The first one is a slit, so 2 slits. So it's an optical component which has 2 vertical slits. And the second one is a razor blade that I will use in the second instance. So first, let's send the laser through the 2 slits, and let's see what it looks like on the screen. So I should have this interference term that we talked about. So I should see a series of bright spots and dark spots, which, by the way, so far you can get the same thing if you were to use water. With water waves, we get the same thing because it's a wave issue. But we will see just after that that you can do that at the single photon level too. And that is not as intuitive. But let's do that first. So now, I'm going to put the laser on. There you go. And you can see here, you can see the interference terms. I hope you can. You can see a series of dark and bright spots. Okay? So this is exactly what I calculated now, where I have the intensity, which is the sum of the 2 intensities times this interference term, which gives us this pattern. But the thing is, what I can do now is I can try to block one of the slit. That's what I'm going to do with the razor blade. And if I block one of the slit, then the interference pattern will disappear, right? Because I only have the light going through one slit or the other, but not both at the same time. So the wave only goes to one channel, doesn't go to the 2 channels, so there's no interferences. So what I'm going to see here is when I block one slit, so the S1 or S2 source with the laser, then what I should get is only a bright spot, which is like light going through an aperture. So let's do that. Here we go. So here I moved the razor blade so that the razor blade cuts one or blocks one of the slits. And what you see here is not exactly a single bright spot. I'll tell you why there's not a single bright spot. But you see one big bright spot. And that is because now the light goes only through one of the slits. So there is no interference terms because you blocked one of them. And we just saw on the calculation that basically that means I1 or I2, one of the 2 intensity, goes to 0. So there is no interference term. It's only I equals I1. The reason why, so this is some physical reason, the reason why you can see ripples here is because we have a slit and we still have optical diffraction. So what you see here is optical diffraction, which, by the way, is also an interference effect. But this interference effect is a single slit interference effect. It's simply due to the fact that you have an aperture. In optics, when you have an aperture, you have diffraction. Not just in optics, by the way, in water too, with water and apertures. But this is a single slit pattern of light. Now, if I pull again the razor blade, oops, then here we go. So the razor blade is moving away from the two slits. Two slits are being illuminated. They interfere, and I have this pattern of bright and dark spots. Okay, so you say, okay, but that's nice, and so what? Well, two so whats. First of all, so before talking about an entangled state here or a superposition state, let's assume now that our light source, so here I used the laser, but let's assume that I have something that can send one photon at a time. Light is made of photons. So let's assume that I have a source of light that sends one photon at a time. So here is what it would look like after a few exposure times. So first, so here are 4 pictures of a screen, so same equivalent screen of my white box here. And this is exactly the same experiment, except that now I send one photon at a time through the slits. And so what we see is that, well, we see on our screen that there are some white spots here, which is where the photon has arrived on the detector. And sure enough, they look like random spots. Okay, one photon goes here, one photon goes there. There seem to be no particular pattern followed. Then I wait for longer, I do the experiment for longer, and trust me, it can take a very long time. You have more spots. Now it looks like a nice sky. Then you wait even more. Then you see more spots on your detector. But now you can start to see that there is some form of pattern coming up. And if you wait long enough, then what you see is actually this. And now clearly, you see a series of bright and dark lines, which is the exact equivalent to what I showed you here. Except that what I showed you here was at the wave level, where I sent a single wave split into 2 and recombined on the screen to have a perfectly understandable wave physical effect of interferences. But here, I have the same conclusion at the end using many, many single photons, so using many times the same experiment where I use the same system. All I do is send one photon at a time to the system. But what's striking is that as many photons can make a wave, is that, well, what's striking, but at the end makes sense, is that, well, the photons have the same pattern as they were to have if I had a lot of them in a single beam like I had with my laser. And sure enough, I end up with the same interference pattern. So I can show you, we'll see if it works. You can find this on the internet. But let's see, so here's the same thing, it's a small movie. I put the reference here, but there are many other references on that. And what you can see is, what you will see is the screen here, so you'll see the impact of the photons arriving at in time. And you will see the number of photons per pixel. So if I were to take one line here, and I looked at the distribution of photons arriving on one line of the detector. And what I should see is this interference pattern of bright spots and dark spots. And that's what we see. If it works, obviously, yes. So you can see, like I showed you in 4 images, where first it looked like the spots were random, And then as you wait long enough, you see that they're not random. That all the photons somehow to be following the same pattern, which is this interference pattern. And so in this case, again, so the reason why we have decreasing in the pattern is because there is, as I said, also a diffraction effect. But never mind this. This is a very optical, physical effect. And here we go. After some time, you have this nice interference pattern, which you would have done, which I did very easily here with a laser, with loads of photons, loads of light, which I can treat as a wave, which I did, in fact, before I erased it. So, now you say, okay, and so what? Well, now here we go. We have our qubit. Because what I'm saying here is that when I am at the single photon level, what does it mean? Well, it means that basically, at a single photon level, one photon went through both of the slits at the same time. It had to go through both of them. It had to follow the same pattern as this one, well, if it were to be the correct formula, as if I were to have two waves. And I can write this qubit state as a superposition state. Either, I can write it as a superposition state or as an entangled state. I will tell you why. So let's erase this. Because now what I've created is a spatial superposition of my photon, my single photon, one at a time. So S1, S2. And then my photon on the screen here of having been through this slit and this slit at the same time. So spatially, now the qubit that I created is a spatial qubit, which is that the photon has gone through either the whole one, so I can write it as in, say, like this, for one photon aperture 1, plus one photon aperture 2. Let's not forget to normalize this, but it doesn't matter. And this I can rewrite it as, say, well, let's call this my state 0, and let's call this my state 1 for our qubit. And here we go. I've got the qubit 01 of the photon going through this one and this one at the same time in order to arrive on the screen and give me the interference pattern that I would have when I accumulate many, many, many photons, which we just did. Well, we saw we did. So in order to have this qubit, which is the sort of maximum qubit in a sense that is, remember, the probability of having one state or the other, is I can just simply take identical slits, which is what I had there earlier. I have identical slits, so the photon can go through one or the other the same way. I just talked about probability, so we can see that as probabilities. The probability is that I have a 50% chance that the photon has gone this way and a 50% chance that the photon has gone this way, but I don't know which way it's gone. So all I can say is that it went through this one and this one with 50% chance. So if I take this squared, so one half, so 50% chance of going through this hole, or 50% chance of going through this hole. And the thing is, if I want to know which aperture the photon went through, I would do exactly the same. I would try to block here and see if it went through this aperture. But of course, it's going through this aperture because I blocked the other one. But I don't have any interference effect anymore. So there is no answer to that. is that if I want to know through which hole I have, so through which hole the photon went through, then I change the system. I don't have the same thing. I had one slit, as before I had two slits. So there is no win-win situation in this case. And again, this is a nice example of the wave-particle duality, where if I want to look at the particle behavior, so know exactly through which hole the photon went through, then I lose the wave behavior because there's no more interferences because I blocked it. So there cannot be interferences. We saw it earlier. Well, I demonstrated it. Where is this one or this one? So there is no, so either you choose the wave, you choose to measure the wave behavior or the particle behavior, but you can't have both. There is no free lunch. But that's good, because that means that we have a superposition state, we have a qubit state by being simply, so if I can write it, so if the photon goes through 1, he hasn't gone through 0, and if the photon goes through 2, he hasn't gone through 1. So I can rewrite this as an entangled state, where now the two properties are 1 and 2, which is 0 photon going through 1, 1 photon going through 2. Let's try it, let's do it like this. So 1 photon going through 1, 0 photon going through 2, or 0 photon going through 1 and 1 photon going through 2. And all of this with an equal probability. So this is an entangled state, right? One of the Bell states. I'll put a minus there, or plus here, doesn't matter. It's just a phase term, doesn't matter, but it's one of the 4 Bell states I mentioned earlier. One of these entangled states of 1, 0 plus 0, 1. Now, I can do that with 2 slits, but I can do it with 3 slits. So 3 slits, it would look like 1, 0, 0 plus 0, 1, 0 plus 0, 0, 1. Which is what? Which is 1 photon goes through one of the 3 slits at the same time. I can do that, like I can do it with water and a laser. I would have a different interference pattern, so it wouldn't look like this one exactly, but I would have an interference pattern the same way. So in this case, I have a 3-qubit system, in a way. So I have to be completely fair, though, with you, is that this can be seen as an entangled state, but is usually not the best one would like. The reason is because what we have here is the presence of something and the non-presence of something. That is usually not the best, because not having something is always present. By default, if you don't do anything, you have nothing. So what I'm trying to say here is this is not, as opposed to when we talk about polarization state of a photon, and in fact, the demonstration and the explanation how we get entanglement with polarization, I will talk about later on. This is a much stronger entanglement in a sense that we have clearly 2 different states we can measure, not 2 states which is, well, one is here but not there, and one is there but not here. It's the non-presence of the photon in one place that is not a sufficient, should I say, choice, because the photon is non-present here, but in fact is non-present anyway. So it's not so nice as a state. But nevertheless, we can use this. So this is called spatial entanglement for photons in this case. This is the only system I know that you can use that. And you can still do a lot of things with it. And in fact, so again, I have no particular interest in any of these any of these companies or any of these groups, but you have to know that around the world, people are looking at how to build a quantum computer using photons. So here you have two companies, so PsiQuantum and Xanadu. So I believe this one is in the US and this one is in Canada. And what they have here, so they use integrated optics, and you can see what it looks like. And basically what they have is the setup I just showed you and the one that I showed you before, all of this, but using integrated optics, things that can, that can be held in a small, in your hand, but with many qubits, many photons used as qubits. So here and there, and you can see here all those spikes here coming down are optical fibers to address the optical chip. Or you can have the version here where you have a single photon source. So I'll come back to that at some stage, perhaps. And then you manipulate these single photons. You do all sorts of things, like entangling them or doing all sorts of gates. You prepare them. Then you put them all in line into fibers. You stick them into an integrated optical chip, something that looks like this, where you have all sorts of beam splitters and various combinations to mix. So to do that, basically, but on a much larger scale. So that you can manipulate those states, this spatial entanglement, but not just on one miserable qubit, but on thousands of them. In fact, even up to 10,000 of them. There's no limit to it. So people work on that with different platforms, so here is what we call bulk. Is probably taking, it would probably take the whole table, if not more. But the fact is they can get something working where they can do something useful. In this case, they had what they call a 60-mode ultra-low loss photonic circuit with 60 qubits, and so on and so forth. There are people at MIT working on this, and people from all around the world working on this type of technologies. So, to finish, although I won't address that, but the next part, which will be the first part for the next lecture, is the physical meaning of psi. I guess by now you already realize that this, right here, for instance, this was a mathematical object that we've been working on so far, but ended up to be a very down-to-earth practical object where we have spatial entanglement, where we have here not there, plus there not here. Okay? So it means that even though, like I said the first lecture, in, I don't know, 10 years, 20 years, 100 years, quantum computer scientists, not just computer scientists, but quantum computer scientists will use quantum algorithms and computers and so on, or even you and me will use the quantum computers like we use our computer, and we don't actually know what's inside. We don't actually care. We don't really need to know that there are gazillions of transistors inside working together. It doesn't matter, really. Well, it will be the same at some point for quantum information in quantum computers. So far, it's not the case. You can't take the physics out of it, and that's why we will see next time how we can give some physical meaning to it, and I already mentioned it, where we go from a bracket notation to an integral notation, which is, in this case, the probability to find a system in space and time, which is called the wave function of the system, which, yet again, is what defines any system. An electron, you, me, an atom, anything. And with this, I will stop for today, and I thank you for your attention. Thank you.